In this video, I'm going to use Excel and Solver to fit some data from chemistry involving cobalt. Down here is the name of it. Um, and it's going to be a peak. So it's just going to be sort of some up and down, and I'm going to fit it to a form known as a Lorentzian and let Solver help me pick the parameters in that Lorentzian form. So let's just have a quick peek at what the data looks like. Oops. So insert XY scatter, make a quick graph. So there it is, some peak. And now I'm going to be interested in fitting that to a form. That form has 3 parameters. I'm going to make some room for those parameters. And those parameters, one of them is going to correspond to the peak's height. One of them is going to correspond to the peak's position. And one of them is going to correspond to the peak's width. It's really the half width at half height. And so this is, the height is a y, and these are both sort of x's. And this form mathematically, and let's just put in, I usually just start with 1, 1, 1, which are going to be terrible values, but we're going to do better. Okay, so it is the height times the width squared. It's a numerator, and then there's a big denominator of the wavelength minus the position, and that gets squared, and that gets added to the width squared. Okay, now I'm going to come back and take my parameters, which are C's, and give them dollar signs, so that when I copy down, the parameter stays fixed for the set of data. I may change the value of the parameter, but it does not vary within the set of data. Whereas the wavelength corresponding to A5 it'll go from 400 to 404, and that I want to happen. Okay, so my C's, my parameters have dollar signs. My wavelength does not. It's the wavelength minus the peak position. That gets squared plus the width squared. That's a great big denominator. And then the numerator is the height times the width squared. Going to highlight. I didn't make a header here, so don't highlight that. If you got a blank cell, it can throw it Excel off. So either write something in it or don't copy it when you're making the graph. Insert XY scatter. There we go. And here is our absorbance. Lost track of what I had typed. Absorbance spectrum. Absorbance spectrum. Okay, and let me get do a quick layout number 9, and then take out the fit. And there's another fit in there in the orange, which I'm going to take out in a minute. But this was, I think it was a wavelength. Nanometers, and this was absorbance. That might not be quite the right word, but that's the basic idea. Okay, and I'm going to cut this. I'm way down at the bottom. I'm going to cut my graph and scroll up to the top and then paste my graph. Okay. And let me change one of these parameters. Peak position seems to be around 500. And there is the peak, sort of around 500. And the height is around 0.4. So this is the game one plays. And then the width of the peak is, and it's sort of the half width at half height, but I usually just sort of say 10, and then that's not enough and go 20. But what I really just want to do is get this line by itself so I can delete it. So you can see by playing with this, I can get it pretty close. But that's sort of not what I want to do here. I'm going to go back to 1, 1, 1 to sort of make it terrible. And then let's try to come up with a criterion to have the computer do it. And we'll start off with 1, 1, 1, really crappy, and then we'll see if it doesn't converge. If this iterative method doesn't converge, then we will come back and give it a better guess than the sort of better guess that we just had. But we're going to make a difference between our data and the fit, and we call that an error, a deviation, a residual. And I'm going to come back and square that. So I want them to all be positive, so I can achieve that by squaring that, copy that down. And then I want to add these all up. So I want some measure that reflects all of the errors. So I take the error for each point and then sum them all up. And now I have, this is some measure of the difference, the error between my fit and the data, and I would like that to be small. So I have something that I would sort of to target, to change these parameters, C1, C2, C3, to make this small, and that's where I bring in solver. So I have, that's under data, and here it is solver. Now I happen to have this added in, but if one does not, you go to file, for me on this smaller computer, more, and then options. And then I want it as an add-in. Here is my solver. It's part of the analysis toolbar. These sort of come sort of as a team, but you have to pick, sort of who on the team you want. So you can sort of, you click, if you don't have anything installed, if I didn't have any add-ins installed, this would be blank and I would look for them down here. But let's say I didn't have solver. Let's say I had analysis toolpack, and then I hit go. This, I find it anti-intuitive. I always want to hit OK, sort of like, oh, here's the data streamer. Or else if I said I want that, then click OK, but that's not what you do for here. You click either the analysis toolpack or solver and you say go. And so they belong together. And then I want both solver and my analysis toolpack, and then I can hit OK. So first go, then OK. But I already had it. Okay, so back to data solver. I happen to have this highlighted when I went to solver, but if not, I choose, this is the thing, this is my objective, this is my target, and I want it to be minimized, not maximized. It's a positive definite quantity, so I could say I wanted it to have a value of 0. That should have a similar effect to minimizing. And then what cells am I varying? These three, the height, the position, and the width. And I'm going to say I'm not going to apply any constraints. If something goes wrong, if one of these things ends up to be 0 or negative, then I'll come back and I'll apply some constraint. But let's try to do it without a constraint. Let's see how it does. This is a very bad guess. So if it doesn't converge or goes crazy, then we'll come back and we'll start it off with a better guess. But it's said it performed 5 iterations in which the objective did not move significantly. So let's see what it did. So here's what it did. It moved the height to about 0.394, with the peak position to about 500 and the width to about 50. And that all seems pretty good. So I'm going to say, okay, keep that solution. And there we go. Now you can play games and say like, oh, it didn't, there's some stuff going on. I should have maybe cut off this peak at like maybe 600 or something like that. So I could have taken this sum and said, oh, here 600 was 55. So I could have said, I'm only interested in going to 55, not 105. And I could have done it, repeat the process. It's not going to change it that much, but it has some effect. So you know, sometimes you have more data, like we're fitting a peak, and you could argue that this data over here, sort of after the 600, is beyond the peak. Don't use it. And I did use it, but I have played this game before, and it didn't have that much effect. So I'm just going to leave it as is. But that's what I wanted to show you, sort of. I have the data as a function of some variable, so absorbance as a function of wavelength. I had a mathematical form, in this case, the Lorentzian. It had some fit parameters. We come up with a criteria, so some kind of measure of error or deviation. We wanted to square this, so this is known as a least square method. We're squaring the error. And then since we want all the points to be in our consideration, we sum them up. We could have, there are variations on this game. You could have done an absolute value here instead of squaring it. But this is a common one, the least square. That's what I wanted to show you. Thanks for your attention.